It's great to have everybody for theory lunch again. Theory lunch means that in theory there is going to be lunch. It's great to have it after 2.5 years that we didn't have it. And we have today Pei Wu from IAS. He did his PhD at UCLA. He works on the communication complexity, query complexity, analysis of the Boolean function. For example, we had the separation, optimal separation of quantum and classical query complexity, and today we will talk about analysis of Boolean function.
Thank you. Really, to be here to give this talk. Thank you for the. So the title of the talk is Random Restrictions of Boolean Function. So maybe let me give a quick background on the title of this talk. And I should also mention that this is joint work with Alden. By the way, can you hear me? First, input. Oh.
I don't think it matters. Oh,
Share slides for me. Okay. Yeah. So now you can connect to the screen.
Yeah, no problem, no problem.
Okay. Cool.
Okay.
Yes, I'll move the. Okay, cool.
Okay. So I guess I should just restart. So the title of this talk is Random Restrictions on Boolean Functions with More Influences. This is joint work with John Alden and Avi Victorson. So now let's actually start by reviewing some of the keywords in the title. The first word is influences. What is influences? It's the following. So influence of a variable xi for this Boolean function f is just the probability that you flip your function by flipping this variable xi over a uniformly random input. And then the max influence is just the max over all the individual influences for the variables. Let's look at some examples. These are canonical examples. So the first one is the majority function. It just output the majority bit of the input. And for this function, its max influence is in the order of 1 over square root of m. We can verify this pretty easily for any input to be sensitive, meaning that by flipping this variable, you flip the value of your function. It has to be the case that your entire input has a essentially equal number of zeros and ones. The number of ones in your input and number of zeros in your input differs by at most 1. And condition on that event, a fixed variable will be sensitive with constant probability, a probability close to half. So that's what we write down. And for a uniformly random string, it has essentially equal number of zeros and ones with probability 1 over square root of n. And that's the max influence for majority function. And then another example is this Tribe's function. It is a CNF formula whose size is n over log n. Size means the number of OR gate. And its width is log n minus log n, meaning that the input to each OR gate is of this length. Okay, and these parameters are chosen so that over random input, you output 0 or 1 with probability close to half. And the max influence of Tribe's function is log n over n. We can also verify it pretty quickly. So it suffices to just check the case when the output is 0. And when the output is 0, you can compute that there is a constant probability that there is exactly 1 OR gate that outputs 0. And all the input to this OR gate will be sensitive. By flipping any input to this OR gate, you flip the value of the Tribe's function. Okay. And conditioning on this event, then you can see that for any variable to be an input to this OR gate, it has probability log n over n. And that's the max influence of the Tribe's function. So for these two functions, they have this property. First, the max influence is very small, is in fact polynomially small. And then the variance is very large. They are balanced, they are balanced functions. The output 0 and output 1 with probability of about half. And in this talk, we are going to be interested in the class of functions satisfy these properties. So it may look like a very restricted class of functions, but let me convince you, they actually arise very naturally. The first scenario is in the social choice theory. So for example, you and your friends want to hang out together during the weekends, and you want to decide whether you want to play at home or play soccer outdoor. Each of you will have a preference, and you want to aggregate your preference and decide what to do during your weekend. Probably you will just do what the majority of people likes. But you can use other functions. For example, when we elect the president, we have this kind of weighted majority over the states. And for each state, we have this majority on the votes. So that's a majority composed with majority function. And in a lot of the situations, we want this aggregating function to satisfy the property that no individual should have the power to decide the outcome, regardless of other people's preferences. So this is kind of captured by the notion of influences. Okay. And then the second motivation comes from hardness of approximation. So you probably know that to prove NP hardness for some approximation problems, a key ingredient is to come up with a dictatorship test. That is to distinguish a dictator function where like one of the variable will decide the outcome of your function, or the functions where every input has more influences. So hopefully at this point, I've already convinced you that this is indeed a natural class of functions to study. Okay, another keyword in our title is random restrictions. Probably you are all familiar with it, but still let me very quickly review it. So like here let's say we have a p random restriction, which means for each variable, we will fix it with probability p. And it will be fixed to a minus 0 or 1 with equal probability. And then with the remaining probability, we keep the variable alive. This way, we get a subfunction of the original function. And we can study the subfunctions. So in this talk, we study the natural problem. So when we apply a random restriction to a function with small individual influences, then what is the smallest alive probability we can set so that the resulting function, the restricted function, remains non-constant with high probability. And we show that you can set this alive probability to be as small as the order of 1 over log 1 over the max influence. Recall that for the majority and for the Trax function that we are interested, their max influence is polynomial small, so this alive probability is about 1 over log n. And this probability is optimal just because the Trax function that we have already seen, the Trax function is a very simple CNN function. It has small width. So by this famous hashtag switching lemma, we can show that if we set the alive probability to be 1 over log n, then it will be a constant function with high probability. Okay. And then we can also strengthen our result by making this non-constant, this quantitative statement of our restricted function being non-constant to a quantitative statement saying that the restricted function will not only be non-constant, it will in fact contains a lot of variance. In particular, we can show that the restricted function will have at least like p to the some exponential on like 1 over the alive probability fraction of the 0 inputs or 1 inputs. Well, whatever this quantity is, it doesn't matter. What matters is it matches exactly the behavior of the majority function. So this is also like optimal in this sense. So now maybe let me give you some context of this theorem. So a related problem was first asked by Kalai and Fricka. So they want to understand random restrictions with arbitrarily small positive constant alive probability. They want to show that after the random restriction with this alive probability, the function will be mildly balanced with high probability. So they, so here we show that this is kind of the case, even if we allow the alive probability to be vanishingly small. Okay, and the client forgot to give this very very interesting name. It N over QX over conjecture. So they come up with this question in the context of social choice theory. And then this conjecture was first proved by Mossel, Donnell, and Oleszkiewicz in their very influential paper called invariance principle. Yeah, but their proof approach falls short to obtain the optimal allied probability. So their approach won't say anything when the allied probability is in an extremal case. Okay, any questions? Sorry? No. I mean, like so I guess the thing is we don't know if we probably should not like say that the AC0 function is also has more max influences and is balanced. Yeah. Well, you can actually analyze AC0. I mean, okay, I don't know if for a specific function you can analyze directly, but in general, I don't know. Sorry?
You don't know that this is
oh, of course, we can't. This is definitely not tied for every function. I mean, like this allied probability is tied for types, but it's not tied for say majority function. But like I'm just saying that if you want, yeah, for this general class, this is the best we can do. Yeah, yes. Yeah. Okay. Good question, but yeah, I never thought about this, so I don't know. I don't know the answer. Right, I don't know the answer. Yes.
Instead of fixing bits, you fix some number of linear constraints.
Oh, I see. Yeah, I see. Yes. Yes. Well, I don't know, but it's also a very good question. Thanks for asking. Okay. Okay, so maybe now let me just show you like one application of this result to block sensitivity. So maybe just let me quickly review what is sensitivity and block sensitivity. So the sensitivity of the function f for this particular input x is just number of sensitive bits. By sensitive bits, I mean like the bit that the variable that you can flip to flip the value of your function. And then the block sensitivity generalizes the notion of sensitivity in the sense that now you can not only flip a single variable, you can actually flip a block of variables. So the block sensitivity for input x is just the maximum number of disjoint blocks that you can flip to flip the value of your function. And then a corollary kind of immediately is that for any functions within this class of our interest, the block sensitivity will be large almost surely. By large, I mean at least log 1 over the max influences. So for majority, it's log n. So you should note that such a result should not hold for sensitivity. So again, just by looking at the majority function, you'll realize that for most of the inputs, there is no sensitive bits. And also note that it is known that or it's really easy to establish that the average block sensitivity is at least log 1 over the max influence by this Conklin linear inequality. Therefore, this corollary is just saying that not only the average block sensitivity is large, but in fact, the block sensitivity is large almost everywhere. Okay, any questions? Yes?
Does it apply for something like the influence entropy conjecture for the transitive case, or transitive means that every two coordinates are the same. So
Yes. I don't know. I didn't try to do this. So I'm not sure. Yeah. But I can try to see offline. Okay. Okay. So let me just show you a sketch to prove this corollary from our main result. So so let's say we just have this random input x, and then what we're going to do is we partition the variables into random blocks, m blocks. M is like log 1 over the max influences, and then note that for any fixed block, then the other m-1 blocks together with this random input induces a random restriction with a Lie probability 1 over m. And then we just apply our theorem. We can say that within this fixed block, you can select the variables so that you get a value that's different from the current input. That means so within this fixed block, there is a sensitive block. And you can apply this argument to all the n blocks. And you can see that with high probability, every block will contain a sensitive block within it. So like that kind of says that for with high probability and random input, we'll have like m divided by 2 sensitive blocks, for example. Okay. So now let's move on to the proof of our main result. So in this proof, we will study some random processes, and we will relate these random processes with random restrictions. And first, let's say we re-encode our input by -1 and 1. This doesn't change anything. And also, we should think that this function not only applies to inputs within the Boolean hypercube, it will also apply to vectors from the real numbers by just looking at the multilinear extension. And the first random process is the following process. So we just consider that we have a random permutation on our variables. So that gives a random order of the variables. And in the beginning, we have no information about the value of these inputs. But these inputs will come in order based on this order. And when it shows up, we reveal its value, and its value will be set to -1 or 1 with equal probability. So for example, like in the beginning, we have no information about any variables. We just let the string to be the 0 string, 0 to the n, using 0 to mean that we don't know the value of the variables. And let's say at time 1, the 6th variable is revealed, and let's say its value is set to be 1. And maybe at time 2, the 3rd variable will be revealed, and it will be set to -1, for example, and so on. So in this way, let's make a few observations. First, at any time t, we fixed like t random variables, with random assignments. So that kind of induces a natural random restriction on our function. And if we look at the endpoint, so at time n, we actually have a uniformly random element from the Boolean hypercube. So that's why we call this process uniform process. If you evaluate your function on the point at time t, then what you get is just the expected value of the function, of the restricted function at time t. This can be easily seen by just checking the case for t equals to 0. And at time 0, when you plug the 0 string into your function, what you get is just the constant term of the function, which is the expected value of your function evaluated on the hypercube. So basically, for the same reason, you can see that fxt is a martingale, because if you set a variable to 1 or to -1, their average will be just to set a variable to be 0. Okay. So making these observations kind of shows you like why the random process is a natural way to study random restrictions. And next, we want to modify this uniform random process a little bit. We just modify the probability distribution when we reveal the value of a common variable in a way such that in the end, we should sample uniformly random element from the preimage of 1 for this function f. And if we want to achieve this task, what is the probability distribution we should choose to design? We can just make the following very simple calculation. So if we set the common variable to be 1, then conditioned on the variable being fixed, the probability, like a uniformly random string we get in the end to be 1 is exactly the expected value, is exactly the function evaluated at this point. So E is the vector where only the corresponding entry is 1. Other entries are 0. And similarly, if we set this variable to be -1, then conditioning on the variables being fixed, the probability that eventually we get an element that is 1 is exactly this value. And we definitely want to assign the probability mass so that that is proportional to these two quantities. And that's how we get this value. And then we just simplify this formula a little bit. We simplify the denominator using the martingale property. So we write the sum as twice of the value evaluated at the point t-1. And for the numerator, what we do is when we change this coordinate from 0 to 1, we actually increase the value of our function by the amount of the partial derivatives of this variable for this input. So that gives us this distribution to set a variable when it's revealed. So the probability will be half, plus or minus, depending on whether the variable is set to 1 or -1. The partial derivatives of the function at this time divided by 2 times the value of the function at the time. Okay, any questions? Okay, let's move on then. And the second simple fact that I want to mention is that if we fix any path, by which I mean if we fix any realization of the random process, so for example, this realization in the beginning, it's zero string. At time 1, we fix the 6th variable to be -1. At time 2, we fix the 3rd variable to be 1. So for any such pass, the probability that our second process, which we call it the conditional process, follow this path divided by the probability that the uniform process follow this path will be determined exactly by the endpoint of this path. So this is the randomly derivatives of the probability measure that controls these two random processes. So for example, if this path ends up in a point whose value is 0, we expect that our second random process should never hit that path because it's trying to sample a 1 instances. So it should never go to that path. Well, the proof is fairly straightforward, just plugging everything and you'll realize that's the case. Okay, now comes our key idea. So we are going to take the controlled perspective of the two random process we defined, especially the second one, where we want to sample a random element from the pre-image of 1. So the controlled perspective as follows. Let's consider again where again the variables come in a random order, and now a variable will be set to 1 or -1 with uniform probability distribution, only with probability 1 minus epsilon. Well, this epsilon will be you can think of it as the alive probability for the random restriction. So meaning that most of the time, a variable will be set uniformly at random. But then with the remaining probability, with probability epsilon, you will get to decide what's the value of this variable. And your goal is that you want to make sure that in the end, this string is still from the pre-image of 1 of your function. So can we do it? Well, probably as suggested by our discussion so far, what a player wants to do is try to simulate exactly the second process. So the player should try to set the probability distribution when she gets to control the value of this variable to be such that in the end, the process should still sample uniformly random input from the pre-image of 1 for this function. And you can calculate if you want to do that exactly, then the number, the probability distribution to follow should be this number, a half plus or minus the partial derivative of a function at this moment divided by twice the value of a function at this time times an epsilon. This epsilon is used to compensate the fact that there is only epsilon probability you get to control. So this will be a valid strategy, meaning that this will be a valid probability distribution as long as the value of function is way larger than the partial derivative of a function at the time. Okay, and what we do if that's no longer the case? What if the strategy is invalid? In that case, we just give up. So we break from this strategy. And then we switch back to what we do on the second random process. So all in all, we are still doing exactly what the second random process is doing, but we take this controlled perspective. Okay, and here, for technical reason, we will see actually very soon that we will break from this strategy. From the first phase, if either the partial derivative becomes too large or the value of function becomes too small. If neither of these two cases happens, then we know that it's gonna be a valid strategy for us. Okay, so what's the point of taking this control perspective is the following. Let me explain it. So in our control process, what we're doing is before the time that we have to stop we have to stop that aggressive strategy, meaning that neither like the value of the function is too small or the partial derivative is too large. So for that part, what happens is that like only a small number of random variables are controlled by the player. And then what we want to say is that the time tau to break from the first phase, the stopping time, we will call it tau. If this tau is very, very large, very, very close to n, and that means the second phase is very, very short. We can think the second phase, in the second phase, all the variables are controlled by the player. So the total effect is that the total number of variables controlled by the player is very, very few. And now let's just switch to the random restriction perspective, and let's just fix some time n, which is close enough to n. And what we want to say is this tau, the stopping time, will be greater than this n with high probability. And then in the random restriction part, we can say that if we only look at the variables before time n, and that those variables not controlled by the player determine the random restriction. And all the other variables being the alive variables, right? Then when the stopping time is larger than n, it's basically saying that the player can actually select the variables on the alive variables so that the restricted function will be evaluated to be 1 in the end. And if we can do this, we can similarly argue for the function 1 minus f, which means that the player should also be able to assign the alive variables in a way such that in the end, the function should evaluate to 0. So if both can happen with high probability, it just means that for this random restriction, for this restricted function with high probability, it's not a constant function. Any questions? Does this make sense? Okay. Well, you should ask questions. Okay. Anyway, maybe let me just say it again. Okay, so we are just doing this comparison between the control process and random restrictions. And in our random process, like we are running the first phase where there is only a tiny probability that the player gets to decide what's the outcome of the variables. And with the remaining probability, all the variables are set uniformly at random. And we want to show that there are actually a lot of those variables being set uniformly at random before the stopping time tau. And those variables will determine a random restriction. And once that random restriction is determined, what we can kind of say is that in this random process, the player gets to control these live variables. They get to select the values for these variables in a way such that in the end, your function evaluates to be 1 with high probability. And of course, you can do the same argument for the function 1 minus f. Therefore, you will be able to argue that with high probability. In the end, the player should be able to assign the values to the variable to get a 0. And therefore, the restricted function will not be constant with high probability. Okay. So in the next part, what we are going to do is we are just going to analyze this stopping time tau. So we need to show that tau is very, very close to n. And the record, how do we define the stopping time? We say that the process, we kind of say that the process stops either our function value becomes too small or the partial derivatives becomes too large. So we just analyze the two cases. So first we want to analyze that the value of function will remain large with high probability. Yes. Okay. So I don't want, so these are all parameters. Like you need to like yeah, it definitely will depend on the epsilon. I mean, like I don't want to like go into like how you actually select these parameters, because like when you have all the pieces together, eventually you can like try to optimize these parameters. But let's just think that delta is something really, really small, really, really small. Okay, right. So we want to show that the value of the function remains large enough. And how are we going to argue that? It's actually very straightforward. We're just using the fact that for any pass of the random process, if we consider the probability of like our control process following this pass divided by the probability of the uniform process following this pass, the ratio should be the value of the function evaluated at the endpoint divided by f0. And here we are looking for like passes, the bad case, the passes that end up in a point which is really, really small. So this is a very, very small number. And when we sum over all the bad passes, it just gives us this bound. So a small number. Well, intuitively, it should be the case because our control process is trying to sample something in the end from the preimage of 1 for this function. So we should not expect that this pass will hit something that's very close to 0 with high probability.
First, it doesn't get similarly stuck if you're very close to 1. I mean, it's good for us, obviously, but if you're close to 1 and you still step, you don't.
Oh yeah, we don't have to, but we don't have to. I mean,
are you able to? Or?
Sorry.
So in the algorithm,
yes,
you described when you're close to 1, the math you don't.
We don't stop. We
don't have the same problem as around.
Right, we don't have the problem. Yeah, I mean, okay. Maybe let me clarify. So the partial derivatives can also be very large in the end. Yeah, but those things all happen like in the very end of the process, which we don't really care about. Okay. So this is the easy part. And another part is to show that the partial derivatives remain small. And we will similarly use this fact that basically the probability mass of the control process is the probability mass of the uniform process times at most the constant factor. Therefore, if we want to show that the partial derivative remains small for the control process, it suffices to just analyze this stopping time, to analyze the same thing for the uniform process, which is easier for us. So that's what we are going to do next. And here, I'm sorry that we have to switch to a continuous process, but it's essentially the same thing as the uniform process. So let's just define it. So now for every variable, we are going to give it a timestamp, which is a random value from the unit interval 0, 1. And then our process runs from time 0 to time 1. So in the beginning, we still have no information about any variable. They are all set to 0. And then when our time hit a timestamp of a variable, we reveal that variable and it will be assigned to -1 or 1 with equal probability. Okay, so this is really basically the same process. Here, the timestamp serves the role to give a random ordering of our variable. And notice that at time 1 minus epsilon, by kernel bound about epsilon times n, variables are left alive, are not fixed. So we just need to argue that the partial derivatives of our function running on inputs defined by this random process is gonna be small for a very, very long time with high probability. So how do we do this? Let me just explain it step by step. Okay, so on the left-hand side, we say that this t is greater than the stopping time. Then that means at some point before time t, the max partial derivative will be very, very large. And then we take the power of this partial derivative to 2 plus eta, where eta is some small positive constant. Yeah, don't worry too much. And then we relax it by taking the sum of all partial derivatives, since we don't know which partial derivative is the maximum. So we want to show that the probability that the sum of all partial derivatives, taking the power of 2 plus eta, will be small with high probability over the time. And then we just apply basically the Markov inequality or the Dupes inequality for martingales. We can do this because the partial derivative of our function is a multilinear function. And then this is a martingale. And when we take this power, it's a submartingale. And thus we can apply this inequality. And in the next step, we apply this hypercontractivity inequality for random restrictions. So this is a new inequality. And by applying this inequality, we replace this 2 plus eta more by the 2 more. So now let me maybe make a few comments on this hypercontractivity inequality. So what we prove is just for any multilinear function. And if you look at any time between 0 and 1, little t and big T and capital T, then take the expectation 2 plus eta norm of our function evaluated at points at time little t. This is bounded about by the expectation 2 norm of the function evaluated at the point of time bigger t. And as we already said that when we are looking at FVT, this is basically the expected value of the restricted function evaluated over the hypercube. That's why we call it this inequality for random restrictions. Okay, and then for those who are familiar with hypercontractility inequality, the original, the standard hypercontractility inequality says that if we have a multilinear function, we can apply some noisy operator to it. So it becomes a noisy version of the original function. For this noisy version, we can take the 2 plus AR norm, and we can bound it about by the expectation 2 norm of the original function. So it's just saying that if we apply some noisy operator, we have this kind of inequality. And now here, I want to draw this analog that when we are looking at random restrictions, like when we are looking at a time prior to another time, it's like we fix less input, and we can think of it as a noisy version of the input from a later time. If you believe in this analog, it's not surprising that we can prove such inequality. Okay, any question? Okay. So now let's see what this hypercontractive inequality gives us. So it gives us this n out by 2 coefficient here, and we will take this and bound it by the influence of this variable, of the corresponding variable, and we can do this just because the expectation of this partial derivative squared is at most the influence. Well, if you want to see why this is the case, you can plug in 0 into it, and then this is just the partial derivative evaluated at the 0 point, which is just the Fourier character of the corresponding variable squared. That for sure is less than the influence. And you can also plug in t equals to 1 into the left-hand side. Then what we have is just the expected value of the partial derivatives over a uniform input from the hypercube, which is if the output of the function is -1, 1, that's exactly the influence. And here it's similar; it's less than the influence. So that's why we can do this step. Well, and in the final step, what we need to do is just to bound the sum of the expected value of all the partial derivatives squared. And this I claim can be bounded by 1 over 1 minus t. And to see this, let's just first think of the restricted function at time t. And if we just sum over all those random variables that are not fixed at time with t, then that's like just the summing up the squared Fourier coefficient of those variables for the restricted function. That's bounded by 1 by Mossel. And also note that at time big T, for a variable to be alive, it has only probability 1 over t, 1 minus t. Yeah, so the right bound for this entire sum should be 1 over 1 minus t. Okay. Okay. So all things left is just to choose the parameters correctly, and just note that on the right-hand side we have this term max influence, because we know the max influence is more from the beginning. Therefore, the right-hand side must be small. This probability must be small. Yeah, the partial derivatives will remain small over the time. So if we want to make very quick summary of this analysis, we're just saying that the max influence will control the partial derivatives of this random process over the time. We know that the expected value of the partial derivatives will be small. And then by the hypercontractivity inequality, we will be able to say that not only the expected value of the partial derivatives, small, in fact, they are somewhat concentrated. So, so that finishes the proof, like why this stopping time should be large. And all in all, it just proves our theorem. Any questions? I don't know if I should continue or if I should stop here. Okay. So maybe just let me I don't know. I can actually like very quickly show like how we strengthen the above analysis to actually bound the variance of the function. So not just say the restriction function is non-constant. We can actually say more, and I think that's really the nice part about this approach. So again, let's recall what we did in our controlled process, which is basically the key part of our analysis. So what happens is like in the first part, there are a few places, there are a few variables that are controlled by the player. You get to decide what value to assign. And for the other part before the stopping time, they are set uniformly random. They correspond to the random restriction, the restricted variables. So now I just draw this orange region, which corresponds to the space of the alive variables. And if we want to show that the variance is large, which is kind of saying that our random process, well, which basically chooses a random element for this like variables such that in the end, the input is drawn from the pre-image of one for this function. So this purple region. We want to show that the purple region is very, very large. If we can show the purple region is large with high probability, we can like do the same for its complement just by analyzing 1 minus f. And these two together will tell us that the restricted function is not only like non-constant, but actually far from being constant. Well, to show the purple region is very, very large, we were just going to bound the KR divergence between these two. For those who don't know KR divergence, it's just this quantity for this case. It's just the size of the alive variables minus the log of the size of the purple region. If the purple region covers the entire orange region, then this is 0. So we want to give an upper bound for this KR divergence, which eventually will tell us that the purple region is really big enough. And here I'll just show you some calculations just to analyze the expected value of the KR divergence. So in fact, we want to show the KR divergence is large with high probability, but let's just focus on the expectation, and it contains all the important piece of the analysis. So now GN denote basically all the information except how the player assigned the variables. And we expected over all those things and try to bound the KR divergence between what is generated of our controlled process and what's generated by uniform process. And in the first step, we just take the chain rule for the KR divergence. And for all the variables, like before the stopping time, we were just bound the KR divergence for each variable. And for all the variables after the stopping time, we bound them all together. So what we will do is basically, let's just consider some time exactly before the stopping time. And then by our definition of stopping time, it tells us that the value of our function at this point is large, which means that condition on the fixed variables at this time, there are a lot of strings that you can assign to the aligned variables such that you end up being one for the function. So that means like if we condition on that part, then the purple region is large enough compared to the orange region. Therefore, this KR divergence cannot be too large. And then for the remaining part, what we do is we just try to do the computation in brute force. So like for each time t before the stopping time, with probability epsilon, you get to decide the value of the variable. And when you get to decide the value of the variable, you know, like there are n minus t plus 1 variables that could come for you to reveal. So for each variable, for each such variable, you can compute the KR divergence because we know the distribution. And we calculate that exactly, and we can show that it's bounded by the partial derivative of the function evaluated at the time divided by of the value of the function, and that's squared. And then next, we apply this inequality due to Talleyrand, which is now often referred to as the level 1 inequality, which says that for any like multilinear function, the following is true. Take the partial derivatives of the function evaluated at point 0 squared, which is just saying that taking the squared first order for coefficients, they are bounded about by the expected value of our function squared times log 1 over G0. Well, we just plug in this inequality and we see that it really fits very well with what we have. Like this term gets canceled. What's left is just log E over the value of function evaluated at the time. And as suggested, the time is before the stopping time, so we know the value of function is large enough, so we can bound it. Yeah, so like everything that just works out very well. So that's, I guess that's all I want to discuss with you for this talk.
So have you tried applying this logic to Arizona finance conjecture?
Oh, we don't know how to do it.
Because there you have a logic degree something, so it should.
No. Here it's a Boolean function. Here it's a Boolean function. And
where do you use the fact that it's a Boolean function, not just bound?
Let me think.
high variance.
Yeah. We need the variance. Yeah, we need the variance.
But there you start with the high variance function of that is low degree, so there's some behavior restrictions, which hopefully isn't compatible with this behavior. So if it has small max influence,
yes,
this all would describe, hopefully it's incompatible with the and still bounded. So it's easy to deal.
okay. Well, at the moment, I don't know what to, well, how to comment. Sorry.
That's something. So I guess the quick question is that
Yeah.
it's
So
not clear what.
yeah, it's not clear what we can do about this approach to the Aron-Selman bias conjecture. Yeah, that's the short answer. Yeah.